Okay, for the next 2 weeks, we are going to talk about a new topic, which is language model. Okay, the purpose of a language model is to trying to transform your text-based data to vector-based numeric data, so that you can use those numeric data to perform further classification or cluster. You can apply any algorithms we talk about in the class to classify them. However, how to transform the text-based data to a vector? There are several different ways, but language model is very important techniques. And of course, there are several different language models. So we'll talk about some basic language models at the first place and talk about how to modify them to some important application in cybersecurity. So as you can see that it is web page provided by TensorFlow. It is called embedding protector. So as you can see that there are several different dots in this space. Okay, so take a look at the left hand side. It says word2vec 10K. That means in this space it has 10,000 vocabulary or words. Okay, in this space, and the algorithm we use here is word2vector. We'll talk about word2vector later. And this word2vector will transform all the 10,000 words into a 200 dimension. It's right here, okay, at the top of the page. The dimension is 200. So every single word will be projected to 200 dimension space. And as you can see that since we cannot show 200 dimension space, so at left hand side you can see that we use in this page you use PCA to to perform dimension to reduction to only 3 dimension. For this 3D space, it only has 8.5% variance of the original 200 dimension. And as you can see that each dot right here is a word, so you can simply just click one of them to see the word in this space, and it also shows the neighbor words. For example, this word is corporation, right? So at the right hand side, you can see that the nearest word of this corporation is company, incorporation, companies, LTT, and so on and so forth. So that so that you can see that in this space, okay, it tends to project the word with similar meanings, similar semantic meanings to close subspace. Okay, and for example, you can see that it's for, right? So false, try, need, expect, unable, reasonable, perform. They have similar semantic meanings. Okay, so but how this algorithm word2vec works? So let's take a look at our class note or number 6, which is language model. So here we have Python example to show you how to perform word2vec. Okay, but before that, here is the picture provided by the word2vec paper. Okay, we have 2 different structure. One's called Hsiao, the other is skipgram. Okay, we'll talk about how Hsiao works. Okay, the skipgram is similar. Okay, as you can see that when we learned English, okay, for example, in Taiwan, English is our second language, right? But in order to understand English, this language, okay, there is an important way for students to test if they understand vocabularies, syntax, semantics, grammar, right? One of the important thing is cloze test, right? So language model, okay, at the first place, they when they design how to use how to let AI or neural network to learn English, the basic concept, the basic idea is to teach the neural network to learn how to do cloze test. Okay, so at left hand side, let us say an example. So you can see, okay, we can use this x1, x2, x4, x5. Okay, so we can use Wikipedia or any corpus to select a lot of different training data, right? So in this example, okay, we use those corpus to find 5 consecutive words. Okay, so that it should be x1, x2, x3, x4, and x5. But since it is a training task, right? So we choose the middle one, x3, as our target. So that means give the for this training data only we given x1, x2, x4, and x5. Okay, and we ask the neural network right here. There should be some neural network right here to help us to output the most possible vocabulary of x3, okay, which is a red y right here. So we can collect thousands, billions of this training data and train this neural network to do cloze tests. Okay? But at the first beginning, to perform such kind of design, the first thing I'd like to say is the very first thing is you need to build a dictionary. This dictionary contains all the possible vocabularies in your data set. So for English, this dictionary should be at least 3,000 vocabularies or words in this dictionary. Okay, of course you can extend your dictionary to 6,000 to 10,000. It really doesn't matter. Okay, but at the first place you need to make a dictionary. Okay, it contains enough English words. Okay, but as we know, English word is far more than 3,000 words, right? So because there are some words which is rarely used. So for the simplicity, okay, you can choose a size, for example, 3,000. And for these 3,000 words, okay, there should be 2 special token used in this dictionary. Okay, the first one should be pad. That means padding. For example, if you collect a lot of 5 consecutive words, okay, and you would like to perform word prediction, right? But sometimes for the corpus you have, maybe for some reason it has only 4 words. Okay, so at the x5 you can use pad, PAD, to replace x5. So it indicates we have only 4 words. Okay, so use the first 2 and the 4th word to predict the 3rd word. Okay, and x5 is padding. Okay, so one of the special token is padding. Okay, the other word should be unknown. Unknown means, as we mentioned, it is impossible to include all the possible English word in this dictionary. So if there are some rarely used word, okay, you can replace the rarely seen word by this unknown token. Okay, and the next word, okay, should be the most frequently word used in English, right? There should be the, right? There should be and so on and so forth. And in all the dictionary, you have 2,998 most frequently English word used in your corpus, and you have two additional token. One is padding, the other is unknown. So that you can use these 3,000 words to represent to use it to represent all the training data in your corpus. Okay, and as we mentioned before, it is very difficult to represent a word by using a vector. So sometimes one-hot encoding is still necessary. So for example, if padding is the first word, we mark it as 0, and unknown is the second word, we mark it as 1 and 2 and 3 and so on and so forth. So at least you have the last index should be 2,999, right? And for training data, let's just use a very simple example. For example, x1 is this, x2 is, and y is the word you like to predict is and x4 is a good, and x5 is book. So maybe you collect 5 consecutive words from your corpus, and that is, this is a good book. So this task is to use this is good book to predict y, which is a. Okay, so in this case, the first place you still need to transform your token, okay, which is this is good book, by using one-hot encoding. So you need to refer to your dictionary. Okay, so for example, maybe the next word is. Okay, so the index is 4, right? So you can use this dictionary to convert your vocabulary, your word, to one-hot encoding. So if that is 4, then you use one-hot encoding to replace is. So it should be something like this, right? One of the vector is one of the item in this vector is 1. It represents the one-hot encoding of is, and so on and so forth. You can use. There always should be one. Okay, you can use this dictionary to encode your original token. Okay, original. And for that means we should output ideally, okay, this neural network should output 001. 00010 to represent the output should be A. But as we, it's very similar to classification, right? But the classification is you have to output this value, okay? But the size of this vector is 3,000, okay? It's 3,000 because you have 3,000 words in the dictionary. And of course, very similar to classification, okay? At the last, you should perform softmax to select the item in this vector, okay, which is the largest one, and you perform argmax, and then you look up the dictionary to see which index has the highest value of the softmax, and that is the output. Okay, so that is, and of course you can design your neural network in any structure. Okay, but in the original paper, okay, it's very simple. Okay, it originally, okay, it has a weight right here. Okay, let's say it's W. Okay, and these 4 weights is the same. Okay, they are the same. Okay, and that means you use the one hot encoding and product it with that orange weight, and we have 4 different input, right? X1, X2, and X4 and X5. So we have 4 vectors. Okay, when we apply X and Y, okay, we write it in this way. And after that, in the original paper, they simply just sum up the result. Okay, sum up the result. And of course, after that, we need to output another vector which has 3000 dimension, right? And perform softmax, something like that. Okay. So we have billions of training data. So that training data will help us to find the optimized weight right here, the yellow one. Okay, so that neural network can perform closed test very, very good, very, very well. Okay, although that is a closed test, but we figure out something. Okay, when we design such kind of neural network. Okay, let's take a look at this one. Okay, and we can see that originally we have a lot of different one hot encoding as our input, right? So you can see that here, for example, okay, that is our first input, and that is our second input, and now this is our input, so on and so forth. Okay, and we don't know the size, and here is the size of the dictionary, right? And as you can see that for the very first word, okay, in the corpus, in the training data, it has only one single one in its entire vector, right? So you simply take a look at the structure. If we have a weight right here, and you can see that if there's only one value in one hard encoding vector right here, you can simply view it as, okay, it simply just select the second row, because in X1, okay, only the second item is 1. So if you times it with the W, and it simply means this X1 simply select the value in W, right? Only select the second row. So we put it right here. Okay, and for the second X, for example, X2, it's one hard encoding is right here. So that means I would like to select the first row in this yellow W, and we put it right here. And so on and so forth, so on and so forth. So basically, of course, this yellow weight is trained by the training data. So originally, we don't know what exactly the W is, but after training, okay, we got the W star as the optimized weight. But it seems like in this calculation, when we perform input and times it with weight, it seems like this row select, okay, the orange one, select this one hard encoding, select this row. This one hard encoding, select this row. So basically, we said that, okay, it seems like the first row, okay, is corresponding one hard encoding, which is this one. That means the first word in the dictionary. It seems like there's some relationship between the first word in the dictionary and the first row in this weight, and so on and so forth. That is the second word in the dictionary, right? And that is the second row selected by this one hard encoding, and so on and so forth. And as we can see that there are if there are, for example, 300 words, and this weight should have 300 different rows, and each rows is represent each word. Okay, so that is the idea of embedding. And of course, after embedding, they perform some other calculation and softmax to there's some other neural networks to help us to output softmax map value to figure out which word should be the y, should be this predict y. But that is some other network right here. But at the first place, you can see that this this yellow vector, it seems like the one hot encoding is related to this yellow weight. And after that, we figure out that we can use this yellow weight to represent each word. So that is word embedding. And that is trained by the training data. So we have the optimized W star. Okay? Although this neural network is designed for closed test, but we figure out the yellow weight is very useful. Okay? This yellow weight can be used to represent each word in the dictionary. Okay? So that is the idea of word embedding, Hsiao, and Shun-Wen has the same structure, has an upside down structure, but it's very similar. Okay, so let's take a look at the code right here. Okay, maybe you can understand it better. Okay, we have a text right here, so we don't have a very big corpus right here. We have only very limited corpus here, just for demonstration. Okay, so the first things you have to do is to tokenize the corpus, because we can see that we have some capital letters. Again, we have some punctuation right here. Basically, the tokenizer will remove all the punctuation and tokenize each words by using the white space and the punctuation. Okay, so after that we have all those tokens, and I believe there are I think there are 60 tokens in this word, in this text. Okay, so that's a very small sample. Okay, so next thing we need to build a dictionary. So for each word we have a number for it. So right here, email is number 1, without number 2, to number 3, no number 4. So after that, if we would like to create one hot encoding for this email, okay, there should be 0, 1, 0, 0, 0, 0, something like that. Okay, so we have a dictionary to specify which word and its index, and of course we have another dictionary which is word to ID, and the other is ID to word. Okay, we can use this function to build this dictionary, these two dictionaries. Okay, so that is the mapping of word. So after that, we can perform one hot encoding. Okay, so we have a vocabulary size of them should be 0, but the word is ID. Okay, the ID are the ID. Okay, the item of this vector. Okay, its ID. The location of this ID should be 1. Okay, that is one hot encoding. So that is just a common way to pre-process this data. Okay, so after that we need to train the data. Okay, to generate the training data. Although in this figure we said that the closed test is to given x1, 2, 4, 5 to predict x3 as y, but actually when we do the implementation, we simply just use the neighboring words to perform the word prediction. That means, okay, if given a word learning, okay, and its neighboring words machine, is, okay, will be used as the word for prediction. Okay, so you can see that after we have okay, you can take a look at this generation function. Okay, but after that I always show you that, okay, we have several different pairs of word. Okay, and so you can see that we have x and y, right? But the x right here only has one word. So we use machine, and the prediction word is learning. The machine, the prediction word is. Learning, the prediction word is machine. Learning, yes, learning, the, right? Because for learning, which is right here, for learning, okay, it has the machine and is. It's its neighboring word. So although the idea is close, but actually when we do such kind of implementation of CBOW and SkipGram, we simply just use the neighboring word. So again, if the word is on, its neighboring word is base and sample. And if you use a larger window size, okay, model and the data will be used as the training data as well. It depends on how many the window size you select. Okay, and this, we only use a very small size. So as you can see that for some word, okay, we have the neighboring word as the training data. So basically, in this case, a word has 4 different training data. Okay, we have 4 different neighboring word. Okay, so in total we have, I think we have 330 training data. Okay, so that is our training data. Okay, it is totally not what we talk about when we talk about the idea, but that is how implementation works. Okay, so after we have such kind of training data, we build a model. Okay, so we have talked about it, and as you can see that the original space, there will be the orange weight. Okay, after that we use this weight to perform another weight, so like we can use this A2 to perform softmax, and this Z will be the perform argmax to find the maximum value of softmax as our output in our dictionary. Okay, and so that is a classification problem, so we simply just use cross entropy to optimize this orange weight. Okay, so after that we have network. Again, network is very simple. we have the input X. Okay, we have W1, we have A1, we have W2, and we perform softmax on W2. So it simply just returns the Z value. So we use this Z value and to look up the dictionary so that we know which word is the largest softmax has the largest softmax value, and check its index so we know which word should be output. Okay. So if you want to run this program, okay, take a look at this definition. Okay. So another thing I think you may not notice that in Python, okay, we have two different ways to perform times. Okay, one is matrix multiplication, the other is element-wise multiplication. Okay, so right here we use matrix multiplication. Okay, so here's a definition of softmax, and usually we have two different ways to perform softmax. Okay, one of the way is simply just this one. Okay, that is one version of softmax, but sometimes you, in some package, you can see that their softmax is a little bit different. It's something like this one. It really doesn't matter because the bigger one always be chosen. Okay, but the scale is a little bit different, but it's okay. Okay, it's okay. So after that, we simply just input all the corpus, all the training data we generate right here, so that this neural network can predict which word is the nearby, which would be the possible nearby words. Okay, so after training, we use cross entropy. Okay, we wish the output word is close to our training data output. Okay, so after that, okay, we can see that after few epochs, the loss becomes smaller. That means the network is trained. Okay, it's well trained. So after that, so here is all the words. Okay, that's all the words, and we can output the W1 as I mentioned. W1 is the matrix. Okay, after the one hot encoding, so that W1 can be used as the word representation. So we have 60 words, right? So we have 60 different matrix. So for each one, okay, you can design your dimension. The dimension we select right here is 10. Okay. So and again, I write the function here so you can check. Okay, what is this word machine? Okay, so it will consult. You will look up the dictionary to see which index it is, and to figure out in W1. Okay, where is its corresponding embedding, which is right here. So that is the embedding of machine. Okay, so think about it. I think it is interesting things. Okay, what we call Hsiao, what we call word2vec. So the result is still this one. So that is the result of word2vec, but it use you can see that it use a very nice corpus. So from the Wikipedia. So the training data is quite large. Okay, and the dimension it chooses is 200 dimension, and it has 10,000 vocabularies in this dictionary. So the result will be much better than our toy program. Okay, but the concept is the same. Okay, and as you can see that since the concept is closed test, right? So in your corpus, there should be some sentence, okay, should be some sentences, and their x1, 2, 4, 5 is the same, but their x3 or y, we say y here, is different. There's always some sentence that its x1, 2, 3, 5 is the same, but x3 is different, are different. That means these two words may be replaceable or interchangeable to each other in English, this language. Maybe these two words has similar semantic meanings, or they are interchangeable. Okay, since they are interchangeable, so that means we have the same input x1, 2, 3, 1, 2, 4, 5, and the output of these two words may be very, 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 maybe very, very similar, which means their softmax value may be very close. Maybe they are both close to 0.5. And that means these two words has similar semantic meanings. And that indicates those two words, if they are interchangeable, they should be somewhere very close in this latent space. Okay? So that is how word2vector works. Okay, we stop right here.